All right, guys, this is our last lecture on hypothesis testing, at least traditional hypothesis testing, using parametric tests. We've talked about between groups ANOVA and within groups ANOVA, and now we need to talk about factorial ANOVA, right? And so the title here for when ANOVA gets big really is intended to imply that the ANOVA design, as I previewed earlier, can really handle not just situations with three groups, but potentially even multiple independent variables, types of independent variables that are both between subjects as well as within subjects within the same exact analysis. And so we want to kind of tackle a little bit of this and to introduce the idea of interactions, which are really only possible to see when you manipulate more than one independent variable in the exact same analysis. Okay, so let's imagine a scenario where you like to ski. Right, and so you're trying to determine whether or not this weekend would be a good weekend to go skiing. So you look at the ski report, and if you're looking at me down there, you can see how sunny and nice it is. It's a terrible weekend to go skiing. But let's say you watch the news all weekend. And every night on the news, the forecaster comes on and he or she tells you the forecast, both for the current week as well as for the weekend. Now, what you tend to notice is that the snow forecast isn't very high. Right? And you don't really notice any difference between weekday and weekend forecast. But what happens if you call the ski slopes themselves? Sometimes they have a slightly different forecast, right? They're actually there at the slopes, whereas the meteorologist is trying to report on this from farther away. Sorry, one of my kids is freaking out because of a spider. So when you look at the two different sets of reports, you might see some data a little bit like this. And let me show you how this is a couple of independent variables at one time. So one of the variables that we're looking at here is whether or not it's a report coming from the ski resort itself or the weather station, right? Two levels, single independent variable. We see on the right-hand side of the graph, we see snow predictions based on weather stations. On the left side of the graph, we see snow predictions from ski resorts. So if you compare these just one to the other, so the way to do that is sort of imagine a spot that's in between the orange or reddish and greenish bars, right? So sort of right in between 1.29 and 1.59 there for the ski resort, and compare that then to about what would be 1.1 for the weather station. You see a relatively substantial difference there that shows that we have an effect of that one independent variable, or at least a perceived effect of that one independent variable, where snow reports tend to be higher when issued from the ski resort than when issued from a weather station. But there's more to it because we actually have our snow reports broken down based on whether or not they were weekday reports versus weekend reports. So if you look at the weather station reports, where they're largely reporting to individuals who are living in cities, living in slightly urban areas, but not necessarily going to a ski resort, right? Their predictions tend to be relatively equivalent in amount of snow between weekdays and weekends, which makes sense, right? The weather doesn't favor the weekend to give you snow. However, if we look at the snow reports coming from the ski resort, we do see a substantial difference between the amount of snow they predict for the weekdays and the amount of snow they predict for the weekends. Now, it makes sense for them to predict higher snow for the weekends because weekends are when people are more likely to be able to go skiing because they're not at work. And so what you see here is an interaction where not only do we have an overall difference between the amount of snow predicted from ski resorts versus weather stations, but you also have a different amount predicted between weekdays and weekends between those. So while there's almost no difference between weekdays and weekends for weather stations, there is a substantial difference between weekdays and weekends for ski resorts. And so the independent variable of weekday versus weekend acts differently when it comes from a ski resort than when it comes from a weather station. And that really is the key to an interaction, when one independent variable shows a different effect at each level of the other independent variable. The question is, who's being accurate in this case? Are the ski resorts potentially elevating their predictions in order to get you out there, and it turns out there's far less snow when you get there? Well, that's a different story. But I think this example at least introduces us to the idea of using multiple independent variables and how doing so allows you to see not just the effect of each one independently, but allows you to see how they may or may not interact with one another. So in an ANOVA, anytime we look at the effect of a singular independent variable, we call that a main effect. When we start to look at how one independent variable behaves differently in the context of another independent variable, then we start talking about interactions. Okay, so I said ANOVAs can be huge, right? We can have one-way ANOVAs, two-way ANOVAs, three-way ANOVAs. Once we have more than 3 independent variables, we tend to start referring to them as factorial ANOVAs. We can then still have a completely between groups ANOVA, where all of our independent variables are manipulated between different groups of people, or we might have an entirely within groups ANOVA, where our multiple independent variables are manipulated within a singular group of individuals. Or finally, we can have what's called a mixed model ANOVA. And you can see that sort of in the graphic over here to the right, where you have individuals going through treatment A versus treatment B. These are different people, right? The A, B, C, D folks are different from the G, E, F, G, H group, one might get, say, cognitive behavioral treatment, the other one gets a more traditional therapy, and then we examine their, let's say, depression levels at time points 1, 2, and 3. And so we have a within subjects variable of time, where we're looking at them at different points in time, and then we have a between subjects variable of treatment or type of therapy in this case. You could run these potentially as multiple studies, right? You could run a study that looked at the different types of therapy between groups. You could look at another study that simply looked at the effectiveness of one therapy over time. But again, examining more than one independent variable at a singular time does offer some advantages. Statistically, it allows us to look for interactions, right? We get even more information than we would from 2 single experiments, where we might see the effect of one variable and the effect of another variable. But it could be that there's not only these individual effects, but a unique way they behave when they're present together. And you can see that then with the interaction effects. The other thing that could be beneficial here is just that it could save time. It could be more efficient, right, to manipulate multiple independent variables at one time in an experiment rather than having to run multiple experiments over time. So there could be several reasons why you end up in this situation. Okay, statistical interactions. Because this is largely the most important thing that you get out of a factorial ANOVA, I want to make sure you get this idea. So here's an example ripped off from your book. Lipitor. Lipitor and Zocor are both medications used to treat cholesterol levels. They also can result in an increase in this phenylencumarins, I'm definitely mispronouncing that, which tend to inhibit an essential liver enzyme. So you don't want to have these increases in these things because then they inhibit the liver, and then that doesn't work out properly, right? And your liver can't function properly. Turns out grapefruit juice can also increase this liver enzyme when present with Lipitor or Zocor. So you've heard of medical interactions before where they say, be sure not to take medicine X if you're also doing Y. Don't take most pain relievers if you drink more than 3 alcoholic beverages a day, and so on and so forth. This is because that the effects of one medicine could be enhanced, diminished, or significantly modified in a qualitative way by the presence of some other substance, right? It's a medical interaction. So let's design a study where we have a group of individuals that takes Lipitor, another group of individuals that takes Zocor, and then we've got a group that has a placebo. On top of that, let's split each of those groups up and have some of them drink grapefruit juice, right? Every morning they'll have a glass of grapefruit juice, and the other group will just drink water. And we'll see whether or not the medicines themselves are having an effect, the grapefruit juice itself is having an effect, or if it's the unique interaction where when both the medicine and the grapefruit juice are together, we have this effect. One of the cool things about ANOVA, as I told you, were the source tables. The other thing you get out of a factorial ANOVA is a table of means and then what we call marginal means. So we start talking a lot about rows and columns and then the individual cells when we talk about statistical interaction. So let's imagine that our columns here, Lipitor, Zocor, and placebo, this represents one independent variable that we might call medication, right? Whether you took Lipitor, Zocor, or you were given the placebo. That column, the difference between those columns, represents the difference in the level of enzyme, right, the liver enzyme, as a function of purely medicine alone, right? And so what we do to see that effect is not look at the cells in the middle of the table, but instead create what are called marginal means down at the bottom of the table. So the level of liver enzymes for Lipitor and grapefruit juice was 60. The level of liver enzymes with Lipitor and water was 30. The marginal mean then would be the average of those two, and that's why 45 is written below that. We see the same thing over there with Zocor with another marginal mean of 45, and then the placebo has a marginal mean of 3 and 3, which is, of course, 3. And so comparing the 45, and the 3 is how we get an idea of whether or not we have an effect, a pure main effect, due to the independent variable of medicine, right? It's simply the columns. Go backwards here, right? The other thing we can do then is look at the effects of the rows, right? The effects of the beverage in this case. For individuals who drank grapefruit juice, when they had Lipitor with it, it was 60. With Zocor, it was 60. And with placebo, it was 3. So the average of those together is a 41. With water and Lipitor, water and Zocor, water and placebo, the average of those will be a 21. And so the difference due to beverage is looked at by examining the 41 versus the 21. The difference due to medication is examined by looking at how the 45, and the 3 might differ. And then when we want to start talking about the interaction itself, whether or not one variable has a different effect at different levels of the other variable, that's when we start to look at the cells. All right? And one way to really sort of visualize some of this is to graph some hypotheticals and see what they would look like. So this is a graph of what we actually end up seeing here in our data, right? So the data we just saw, the 60, the 30, the 60, the 30, the 3, and the 3. What we tend to see here is that if we look at just water alone, so just looking at the red bars, we see that when individuals are purely drinking water, they do have an increase in these enzymes when taking Lipitor and Zocor versus a placebo, right? Those bars are higher, whereas the placebo is much lower. We see a similar difference when drinking grapefruit juice, right? Grapefruit juice goes up considerably from when it was at the low level of a placebo when people take Lipitor or Zocor at the same time. So, and one thing we could then say is that realistically we're sort of looking there at a main effective medication, right? When we move from either water or grapefruit juice, right, which already have their own slight difference between them, when we add medication to it, both go up. So medicine is having a significant effect on the absorption of this enzyme, right? We could also, slightly different data here, these don't reflect our effect, could have looked at, say, just a main effective beverage by itself. If every one of our groups looked just like this, where we had the drop we saw between Lipitor and Zocor, but then we saw a similar drop over in the placebo, then we would have very clearly a main effective beverage, because in each case where we go from grapefruit juice to water, we have the substantial drop in absorption, right? So the beverage itself creating this difference in absorption levels, where grapefruit juice was always higher than water. The other thing we can see, we go back to the way our data actually looked, is the statistical interaction. And one way of sort of observing a statistical interaction in graphing data is to look at the lines and see if they are parallel. So if I draw a line between grapefruit juice and water just for Lipitor, so the top of one bar down to the top of the other, that tells me how beverage changed absorption levels within the group of Lipitor. Now draw the same line over there for Zocor. See that both these lines have these fairly downward slopes. Now do the same thing over there for the placebo. Notice that it's entirely flat, meaning there was no difference in absorption between grapefruit juice and water when you weren't taking a medicine, you were only taking a placebo. What we see is that those two lines over here are nowhere near parallel with this line. There's one that stands out. And that's one way of visualizing an interaction, by graphing it and seeing whether or not the lines are parallel between your independent variable effects. Okay, so in a simple two-way between groups ANOVA, which would look somewhat similar in a mixed groups ANOVA, but we won't be doing mixed group analyses because they're a little more complicated, we still use a source table, okay? And so we use a source table for all ANOVAs. It really doesn't change a whole lot, too. We just simply have to add an extra row for our extra independent variable, and then one more row for our interaction. You then have 3 F ratios because you can test for each of your main effects as well as your interaction. So if we use our previous example, our top row there, the first one is on medication. This would be saying whether or not you have an effect purely due to the difference between Zocor, Lipitor, and the placebo itself. Right? And so we have a sums of squares for medication, we have degrees of freedom, we have a mean square, right? And then down at the bottom we have the mean square within, just like always, so we have that within groups variability in every type of ANOVA. We then have a line underneath medication for beverage. That row corresponds to the main effective beverage, that independent variable. Do we have an independent effective beverage alone, grapefruit juice and water, compared to one another regardless of medication? And then finally, do we have an interaction where the difference between grapefruit juice and water's effects on absorption increases or decreases at different levels of the medicine independent variable? We do, and so we would have an interaction here. But otherwise, the source table looks highly similar to the source tables we've already seen in the past. Okay, let's look at a conceptual idea of a mixed model ANOVA real quickly so you get an idea of what I mean here. Simple example, would cognitive or traditional therapy work better for reducing depression? Cognitive behavioral therapy has been shown to be very effective since it started being used, so it's entirely possible then that it is in fact more effective than traditional therapy, and this kind of design could potentially look at that. Now, to see whether or not therapy has been effective, you traditionally want a within subjects manipulation where you can look at individuals both before and after therapy, right? Did they come in depressed? Did they leave less depressed? If so, then therapy is produce some benefit, right? Some sort of beneficial reduction in depression levels. So we're going to have to measure depression. That's going to be our primary dependent variable. We'll measure depression. We're going to have one independent variable that corresponds to time. That's a pre-test, right, before they come in, right when they come in, before they've had therapy, and then another post-test after they've had some therapy. This is a within subjects variable because everybody gets measured before and after. But we have a between subjects variable as well, where some of these individuals, a good half of them, will receive cognitive behavioral therapy to treat their depression, and the others will receive traditional therapy. Because these are different groups receiving different types of therapy, this is our between subjects variable. Because we have both a between subjects and within subjects variable, right, one of each, we have a mixed model ANOVA.
One of these things is not like the others. One of these things doesn't belong. Can you tell which thing is not like the other by the time I finish this song?
Can you tell? So if you look at the graph, I like this song because well, it's Sesame Street, and because we used to play this game when I was in grad school where we'd look at data and say, which one of these isn't like the other ones? Because that's the condition that's usually interesting. That's the one that's standing out. And if we look at this graph and we say that we're looking at depression levels, okay, we remember we had 4 groups, 4 at least observations. We had a pre-test, post-test for both of our 2 groups, and then our groups received either cognitive or traditional therapy. So all of them are measured on depression. We have 4 measurements then. We have a measurement for cognitive people, both before and after, and we have a measurement for traditional therapy before and after. So if we look at the graph, the solid line is our traditional therapy, so the top 2 dots up there. If you look at their depression level on the y-axis, you see that with traditional therapy, their depression level remains unchanged. It is the same approximate number, both at the pre-test and at the post-test. Now you look at the cognitive behavioral therapy. Their pre-test is just as depressed. That's good. They're just at the same level as the traditional therapy, but when they get to the post-test, they are significantly lower. So which one of these has a different measurement in terms of depression? It looks like 3 out of our 4 have the exact same measurement, right? The pre-post is the same for traditional. The pre is the same for cognitive. It is just that one, that post measurement for the cognitive behavioral therapy that differs from the rest of them. And that's where we start to see the one that's not like the other. That's where we start to see the interaction, right? The non-parallel lines here. Okay, so that's the introduction to a two-way ANOVA. In the next video, I'll show you how to calculate the two-way between groups ANOVA. You won't have to do this on an exam, but there is a homework assignment related to this, and I want you to be able to at least conceptually understand how interactions work as well, so we'll talk a little bit more about that in the next video too.